Scientists are interested in earthquakes because we'd like to be able to do something about the damage they cause, like you see in these scenes from a supermarket in Japan. Similarly, you can see the damage to the buildings during this earthquake in New Zealand, causing bridges to fall and producing fissures in the ground. Actually, there are many consequences of an earthquake, some more of which we'll cover later. One thing that became very obvious early in the study of earthquakes was that there are certain places in the world where they happen and other places where they are rare. This map shows the worldwide distribution of earthquakes, and it's pretty clear there are certain zones where you are quite likely to be involved in an earthquake and others where it seems pretty rare. But how do we know where the earthquakes take place? And how do we know when they take place? Clearly we must have some technique that allows us to figure out what's happening here. This method was developed in conjunction with devices that can measure the motion of the ground. These devices are called seismographs, and we run them continuously, waiting for an event to happen. Nowadays we keep track of the record electronically, but in the past we used to have a device that had a cylinder on it. The cylinder rotated and moved along all day to give us a helical line, and this record is called a seismogram. The record on the seismogram is wiggly, not only because earthquakes are recorded, but also anything that makes the ground move, such as a truck passing by, or the vibrations from a nearby railroad, or the waves crashing against cliffs, and even the noise made by the wind causing trees to shake. When we look at the recording of an earthquake that seemed to have happened a long way from our instruments, we often see that there are three separate groups of vibrations that arrive one after the other. The ones that arrive first are obviously the fastest of all the waves, and they seem to be produced by a motion that makes the ground vibrate in the same way that the wave is travelling. These waves are called the primary waves, because of course they arrive first, or the pressure waves, since they move by a variation in pressure in much the same way that sound waves do. For short, we call them P waves. They tend not to be very intense. Following the P waves, a secondary group arrive. These waves move by vibrations that take place perpendicular to the direction that they're travelling, by a process called shear, rather like ripping a piece of paper. This way of moving is not at all like sound. In fact, it depends upon what you might call the rippability of a material. If a material can be ripped and torn, then an S wave can travel through it. Air and water have no resistance to being ripped, so S waves cannot travel through fluids. Since they are slower than the P waves, they appear second on our seismogram. Finally, the slowest of the three types of waves are the surface waves. We use that term to distinguish them from the other two, which are collectively called the body waves. Body waves travel deep through the interior of the Earth, the body of the Earth, but the surface waves are confined to the surface, hence their name. Not only are these the most energetic of the waves, but they're also the ones that cause the most damage. These relatively simple observations allow us to say something about earthquakes in general. The first observation we can make is where earthquakes occur. Obviously this is quite useful because it helps us to identify risky areas like California. We can do this using the body waves. Since P waves move faster than S waves, the further away we get from an earthquake, the longer the time interval will be between the P waves and the S waves. This time interval is called the delay time. Actually, using data from earthquakes for which we knew the location and time, because there were people there, we were able to draw some standard curves quite early in the study of earthquakes, called travel time graphs. These travel time graphs show how long it takes for the P wave or the S wave to get to the seismograph, depending upon how far away the instrument is from the earthquake. Notice that the gap between the two curves gets bigger and bigger the further away you are from the earthquake. If that was the only information we have, it wouldn't help us very much. After all, we may know how far away an earthquake is, but not in which direction. So the best we could do would be to draw a circle on a map with a radius equal to the distance indicated by the delay time. In this example, supposing we're in Washington, D.C. and our records indicate that the earthquake took place 2,300 kilometers away. Well, we can draw a circle around Washington 2,300 kilometers in radius. If we contact our associates in Mexico City and ask them if they recorded the same earthquake, they may say that it was 2,800 kilometers from them, allowing us to draw a second circle. Finally, associates in Trinidad tell us that the same earthquake was only 1,500 kilometers from them. Thus we can get a third circle. The intersection of these three circles gives us the epicenter, in this case in Port-au-Prince in Haiti. In fact, all this assumes that the earthquake took place near the surface. The location on the surface above where the earthquake actually took place is the epicenter. The actual location of the earthquake, which might be quite deep, that is called the focus. Fine, except that how do we know we're talking about the same earthquake? Well, we can do this by knowing the time at which the earthquake took place. Let's go back to our travel time graph. As we said before, if we know the time delay, we can find out the distance we are from the earthquake, like this. But we can also determine how long it's taken the P wave to get to us, like this. So, using our seismogram, we can read off the arrival time of the P wave and then subtract the travel time given to us from the travel time graph and ultimately end up at the time the earthquake took place. This is sometimes called the origin time. By doing this at the three different stations, we can be sure that we're looking at the same event. Knowing the location and the time of the earthquake is very useful, but there are other basic facts that we'd like to keep track of too. How big are these events? At first glance, how big they are would seem to tell us how destructive they are, but that relationship is not always as obvious as it may seem. Our first attempt at doing this produced what is called the Mercalli intensity scale, which has classified an earthquake depending upon how much damage it did. You can read a little bit more about the Mercalli intensity scale at these two websites. Nowadays, we measure the size of an earthquake based upon a scale called the Richter magnitude scale, named after the scientist who developed it in the 1930s. To do this, we look at the surface waves, the ones that actually cause the destruction during the earthquake, and we measure their peak amplitude. Now, obviously, that amplitude will be bigger the bigger the earthquake is, but it also depends upon how far away you are from the earthquake. The further away you are from the earthquake, the smaller the vibrations will be. So the delay time is necessary here too. We have to put in some sort of a factor that accounts for exactly how far we are from the earthquake. The Richter scale is a strange scale, with an increase of 1, say going from a magnitude 6 to a magnitude 7 earthquake, producing 10 times as much ground motion and about 31 times as much energy being released. Of course, when you go from a 7 to 8, that factor comes in again. And now we've got 10 times as much ground motion as we had for a 7 and 100 times as much ground motion as there were for a 6. 30 times as much energy released as the 7, and nearly 1,000 times as much energy released as a 6. Later on, we developed other measures, such as the body wave magnitude and more recently the seismic moment magnitude. All of them are adjusted to give us numbers that are approximately comparable to those upon the Richter scale. This website gives you a good analysis of the methods.